All right, so today we're going to talk about the last method, which is variation of parameters, which you've seen before with just a singular linear second-order differential equation. The process is going to be a little bit different, although if you watch the proof, I'll post an example of a guy walking through the proof of this and why this is really the Wronskian. Remember, we found the Wronskian and we did the integrals. We're going to do something similar, but the proof of this, I tried to type it out. Like I was trying to it's in a textbook, but it's not user-friendly in the textbook. Like to read through it is not fantastic. So I was trying to make it simplified and I couldn't get it any more simplified than they had it in the textbook. And I figured there's no point in typing it all. So I'm going to ask for some blind faith on this as to why this works. And I'll post a proof of someone explaining it. We have something in math called the fundamental matrix. The fundamental matrix is represented by, you may hear people call it phi. It's usually pronounced phi, but it's this Greek symbol. And the Greek symbol is phi. You may hear phi as well. This is the example of a fundamental matrix. And what this matrix consists of is columns of the solutions or entries of the solution vectors to the system, to the homogeneous system. So if we go through and solve the homogeneous system, which we're finding the complementary solutions, and when we find those solutions and we form a matrix with those solutions, we create a matrix that is non-singular, meaning it has an inverse, and its determinant is non-zero, okay? So this fundamental matrix is actually what we're going to use. So it is important when we're using variation of parameters to actually find the complementary solutions to solve the system as if it were homogeneous first, because then we use those to build a guess, basically, as to what our matrix or our solution to the particular solution looks like. Okay, so in Unit 2, just like we did with variation of parameters, we have to start by solving the homogeneous system. When we go to find the particular solution is, and again, this is where I'll post a video of the proof rather than give it to you. It is where we take this phi multiplied by, this is where it gets a little messy, the integral of the inverse of phi times the part that makes it non-homogeneous, that f of t, that function, that vector that we have, dt. So I'm going to walk you through an example from start to finish. This is an example where I would write small, similar to yesterday, and probably go in columns, but you're also going to want your Symbo Lab open, because we're going to not calculate the inverse of the matrix by hand. You're welcome. It's kind of a pain.
Oh, I was looking forward to that.
I'm sure you were. I'm sure that was what you were most excited about. Okay. So the first thing I'm going to do is solve this as if it were the homogeneous equation. So I'm setting the determinant of a minus lambda I equal to 0. So using the matrix, so we would have negative 3 minus lambda, 1, 2, negative 4 minus lambda, and the determinant of that would be negative 3 minus lambda times negative 4 minus lambda minus 2. And we want to set that determinant equal to 0. All right, so we'd get positive 12, positive 3, positive 4, lambda, bless you,
Thanks.
Lambda squared. So we end up with lambda squared. What did I say? Positive 3, positive 4, plus 7 lambda, plus 12 minus 2, plus 10. So lambda plus 5 times lambda plus 2. So we get two eigenvalues. We get lambda equals negative 5. So if we substitute in -5 into the vector, into the matrix, we would get -3 minus -5 would be +2. 1, 2. -4 minus -5 would be 1. And I'm going to solve that when it's equal to 0. So we get 2x1 plus x2 equals 0, which means x2 equals -2x1. So when lambda equals -5, the eigenvector I would pick would be, I'd probably let x1 be 1, then x2 would be -2. Yeah, good so far? This should not be new. Repeat that process with lambda equals -2. -3 minus -2 is -1. 1, 2. -4 minus -2 is -2. And so we get -x1 plus x2 equals 0, which means x2 equals x1. So with the eigenvalue of -2, the eigenvector that goes with it would be 1, 1. Okay. So we would say our complementary solution looks like this. This is how we've written it so far. We would say e to the lambda t times that eigenvector. Probably we'd put a C1 in there. We'll come back to that constant in just a minute. E to the -2t times that eigenvector of 1, 1. And we know that this complementary solution would really have can have some constant multiplied by that lambda, or that e to the lambda t. So it may say C1 e to the -5t times the vector 1, -2. We good with this? This actually forms my fundamental matrix. Here's what my fundamental matrix looks like. If we define this matrix would be defined by ignoring the constants. That's why I didn't write them here. They have their own matrix that we'll worry about later. This would be e to the -5t, 1, -2. So this column, this first column, would be e to the -5t and -2e to the -5t. Notice this first column is the solution, or the first solution with the eigenvalue and eigenvector. The second column of this matrix then would be e to the -2t, e to the -2t, and that comes from that second solution. And it doesn't really matter what order you write these in. As long as you're keeping each column representative of the solution. So this forms our fundamental set, or forms a fundamental set of the solutions to the homogeneous equation. And it gives us this fundamental matrix. Now we need this matrix, but we also need the inverse of this matrix. And this is where I would use Symbolab or something similar. If you wanted to do a Google search and do an inverse matrix calculator, whatever one pops up should work. Symbolab works really well. Yeah.
What is the inverse of a matrix?
Good question. The inverse of a matrix, the way we calculate it is it's 1 over the determinant. So we find the determinant of this matrix, and then it's 1 divided by the determinant, and then you switch, these two entries get switched. Sorry, it's been a while since I've done one by hand.
The end goal is that the matrix times...
Itself gives you the identity.
Okay.
Yeah. So it's just like when we talk about the multiplicative inverse of 5, it's 1/5. Because it gives you the identity, which is 1. Mm-hmm. Right? The multiplicative identity, which is 1. That's what our goal is. The process through it, though, is you find the determinant, and now I can't remember which one's which. Two of the positions switch spots, and the other two become negative. But I don't remember which order it goes in. of
That's
which one.
okay. It
Okay.
makes sense, yeah.
Can you?
Conceptual.
But it gets messy when you're dealing with functions. That's why I would prefer the Symbolab calculator. And in Symbolab, if you want to use the notation and not just do a Google search, if you type in inverse and then you go to the 2x2 matrix, because this is a 2x2 matrix, and type it in, it will kick back the inverse for you.
What can be more constant?
They are constant. They'll get absorbed into the constants we're gonna create. We're gonna find.
More constants.
There's lots of
So when we
constants.
write the complementary solution, should we still write like C1, C2?
Yeah, so like if you were going to go give me the whole solution to this function, then yes, we would want the C1 and C2 in there for sure. Yeah.
Vectors are always a failure.
Yeah, we'd want the C1 and C2 in there. But I'm not going to do that part right now. Okay. What'd you say, Jake? Sorry.
I said the vectors that we use are arbitrary anyway, so it's
That is true. The vectors are arbitrary. Okay, so the inverse of this, when you type it in, you should get e to the 5t. I may just call this 1/3 e to the 5t. Negative 1/3 e to the 5t. Positive 2 e to the 2t over 3, so 2/3. So it looks like my determinant was 3, 1/3, 3. E to the 2t over 3, so 1/3. So you should get that as your inverse. Not just 1/3, 1/3 e to some power. All right, that's what we need. So now we need to go find my particular solution. And here's what the particular solution looks like. When we go to find the particular solution, I'm going to take that first fundamental matrix. So it's e to the negative 5t, e to the negative 2t, negative 2e to the negative 5t, and e to the negative 2t. And I'm going to multiply this by the integral of the inverse matrix, which is 1/3 e to the 5t, negative 1/3 e to the 5t, 2/3 e to the 2t, and 1/3 e to the 2t. And this is going to get multiplied by that f of t. F of t is this part of the function that makes it, there is integration by parts, yes.
Can I just throw that whole thing in
Yeah, can we
I
just...
don't think I can do this.
You can do this. You are plenty capable.
after you take the dot, you like give it to the result come off on the bottom.
Yeah. Okay, so I'm going to cheat just a little bit in that when I go to write, I'm going to zoom in. When I go to write my particular solution and we go to solve this, I'm actually going to do this in parts. The first thing I'm going to do is I'm going to take this matrix multiplication. This is what I'm going to work on first. And remember, to multiply matrices, those inside dimensions need to match. This is a 2x2. This is a 2x1. This matches, which means my result is going to be a 2x1 matrix. And it's easy to forget what your result should be because it gets kind of messy. Okay, so I know this is that matrix
Where did you get 3t and e to the negative t?
from right here. This is the f of t. Right, so this is equivalent to this. Whatever we have there. Okay, so then I'm going to do the integral of, and now I'm going to do my matrix multiplication. Okay, and remember when we do matrix multiplication, we take this row by this column. So when I do that row by that column, we would get 1/3 e to the 5t times 3t, which gives us t e to the 5t. Right, and then I multiply negative 1/3 e to the 5t times e to the negative t, which gives me negative 1/3 e to the 4t. There is my first row. My next row, I'm going to take and multiply by the columns. So we get 2/3 e to the 2t times 3t, which gives me 2t e to the 2t, plus 1/3 e to the t. And you'll notice now I need to integrate this. What? It'll form a 2x1, but a messy 2x1. This is one row right here. So this is one row. This is one row. So they're independent, like they're not separate terms. Good. To integrate this would be like me taking the integral of just this expression. So I'm taking the integral of just that first row. What you should notice, and I'm sure you're excited about, is this t e to the 5t we would need to use integration by parts. I'm glad you're excited. So
hypothetically, we've lost all willpower to integrate.
Yeah.
What if hypothetically?
I've never had them.
We saw this to calculate.
Yeah, can you give us on their next test, we just give them our integration by parts.
I'm trying to make them feel successful for their
I don't
exam.
know, they could do these integrals, like that's what
That
they're
is
saying.
true. They could do, that's what they're trained to do. Like they're monkeys.
They all can teach them.
We can just, it's just us using that. Like the math we do is
Yeah, you know,
math
like,
majors, it's
that.
like-
You're senior to them, therefore we can use it.
They're just doing computational stuff. We actually have to think, so might as well have them be our computational.
That's true, we could just turn them into a calculator bank for us.
Okay. I'll try that next time. Get Calc BC kids to do all your computation.
Yeah, can we just bring one of them to an AP test and sit them on the table and they can,
Maybe call them our
Well, we don't have any.
Put them in a booster calculator.
that's true.
All right. So if you remember integration by parts, we start with choosing a u and a dv. We take the derivative of u and the integral of dv. And then integration by parts is u times v. So we'd get u times v, so we have 1/5 t e to the 5t minus the integral of v du. I'm going to pull the 1/5 out. V du. And so we get 1/5 t e to the 5t minus, that would end up being 1/25 e to the 5t. And that was just this first term in that integral. We still have this minus that we need to take the integral of this 1/3 e to the 4t. So we'll end up with minus 1/12 e to the 4t. Oh, I've already done the integral. So that is the first row. And we still have to multiply. That's the first row of this integral. Now I need to repeat the process. Are we excited?
No. Can we notice a pattern and just say it's t e to the 2t minus 1/2 e to the 2t?
Oh, yeah.
Plus.
Plus e to the 2 over 3 plus c2. Oh yeah, we're seeing that. Then we don't have
You can ignore the constants again.
Oh.
Let's Let's do what Jake said. Blind trust Jake.
Oh, yeah,
Yeah. Of course we do. See, it's good to question things every now and again.
No.
Don't tell my daughter I said that. Okay, so if we went through the process and we did the integration by parts on this 2t e to the 2t, we'd end up with t e to the 2t minus 1/2 e to the 2t. And then the integral of 1/3 e to the t is 1/3 e to the t. Okay, so what we just found,
Is the thing we then need to multiply by 5.
correct. What we found was this integral right here. So that's what this is. And now what I need to do is I need to take and multiply it by that fundamental matrix. So I'm now going to multiply this by the e to the negative 5t, e to the negative 2t, negative 2e to the negative 5t, and e to the negative 2t. Keeping in mind that really what I have here, though, is a row, right, by each column. This column is this is a 2-by-1 matrix. It's one really long expression, but it is a 2-row by 1 column matrix. As messy as it looks, that's what it is. Okay, so here comes fun. So if I multiply, this would be e to the 5 negative 5t times 1/5 t e to the 5t. That's going to give me 1/5 t.
Oh, it looks simple.
Right? This term times this term is going to give me minus 1/25. E to the negative 5t times negative 1/12 e to the 4t is going to give me, oops, got to go back to the pencil, negative 1/12 e to the negative t. So I multiplied the first term by the row. Now I need to multiply the second term by the row, but it's going to be added to this, so I will now have plus e to the negative 2t times this row down here. So that will be plus t. I can't do both the pen and.
Oh, and after all of this, you have to combine fractions. Seems like a good time.
Why did you do this?
Yeah, do homework problems.
Two homework problems. Oh my god.
Oh.
I still have to bring one.
I don't know where this came from.
Where was our small writing warning?
I did!
This is not enough room. Actually, I have a lot of room left over.
Shut up,
Mark.
Jim.
Look.
If you have room left over, just take
That's
it
a lot.
somewhere else. Yeah, you won't be able to read it when you have to.
Kind of. I can make it out. Like,
What's a half minus a 25th?
It is supposed to be a 12th. It is supposed to be, no, it's not. It's supposed to be a half, sorry.
Combine fractions, and then I'll write down the combined fraction.
It is a half.
Yeah, because I have no more space. I am out of space.
27.
27 50ths. This is a fun number, right?
That's just about 27/50th.
You can borrow some of mine.
Miss Allison, in like even higher level math, are we just gonna have like one problem for homework assignments?
It's 2.
2.
Two. Well, yeah, but like, did you put it less and less?
Yes. Oh, this your last one was only 3. This one's 2.
So our next homework assignment is 1, and then there's no more homework?
That's pretty much it. Actually. Okay. Now we can combine like terms.
I really need to get paper that I can zoom out.
Tests and stuff. Will this formula be like given to
Yeah.
us?
So you have like paper you can zoom out with.
So this test please be like open.
Can this test not exist?
I think this test will likely be combined with your final because we don't have enough time.
That sounds like
I would take that. That works.
When's the CAP test?
Monday the 9th.
So after that day, are we like done? Then
Well, are you in Calc BC?
Well, yeah, like, are we also gonna have the rest of the year off?
Are you in Calc BC?
Here's the thing, Sandon. This is the one class that I would not mind actually having through the end of the year.
That's true.
Thank you.
Because this is fun.
Yeah.
Izzy?
Does
The
the
math
final
is-
include the Calc 3 stuff?
No. It would be just differential equations.
Wait, so
Not Calc 3, not first semester. Okay, this is my particular solution. It is a 2x1 matrix, as ugly as the 2x1 matrix is. So if we were to write the full solution to this problem, you can just watch. You can just watch. We would have C1 e to the negative 5t times that 1 negative 2 plus C2 e to the negative 2t 1 1 plus this loveliness.
And somehow someone found that helpful.
who decided this was space?
Is that a 1/6 e to the negative t?
Who came up with differential equations and can I beat them up?
Here? Yes.
Yes.
I'm guessing they're already dead.
Someone's like, oh, this would be.
I will still beat them up.
That's a little
One of
bit.
the class field trips is leave to piss on it.
Oh, that's recorded. I don't know what to do with that. Oh. I would love to because we'd probably means we could go to Europe.
Let's do it. Let's go to Europe and let's go piss on some old guys.
Apparently there's a math museum in New York. Can we go to that?
Probably like burn that down.
New York's not my favorite place.
Yeah, why would you want to do
New York is kind
I'd rather go to Europe. All right.
It's really drawing you in.
So a bit tedious. Yes.
Just a tiny.
Just a tiny bit.
tedious. No.
All right. Questions on variations of parameter.
Is there a faster way to do all this?
You would not give us any space.
Is there an example?
Yeah, it could have been like, it could have come out
Yeah,
like
isn't there a
T
faster
plus
way that we can
something.
do this that we're not
Could
being
have been.
told yet?
No.
Yeah, at the end of this year, you just like,
Yeah, this
like
Haha, look at
My
all
boy
these
was a
things.
shortcut into this.
There's no shortcuts in life. Isn't that the saying? All right.